In this section, we're going to talk about vector fields. Now, up to this point, we've mostly dealt with functions that associate a single numerical value with every point in the space we're working in. So in single variable calculus, we have a function like this. For every input value, there is a single output value, right? A single numerical value. Or for multivariable functions, maybe we have, something like this, 2x plus e to the y plus sine of z. Okay? For every point in three-dimensional space in this case, there is a rule that tells us that associates another value to that point in space. Okay? But a vector field is a little different. Instead of associating a single numerical value with each point in space, we are going to associate a vector with each point in space. So let me give you an example. Let's say f of xy, let's restrict ourselves to 2 dimensions for now, and for each point xy in two-dimensional space, we are going to associate with that point a vector. And the rule that tells us which vector is associated, let's make it negative y comma x. Okay? So let's sketch out a little example of what this is going to look like. I don't want to get too big here because, as you'll see, this will be quite a bit of work even if we keep this small to sketch this all out. So let's look at a few points, okay? So let's start at the origin, 0, 0. If I plug in the point 0, 0, what vector do I get? Well, I get the 0 vector. Not very interesting. Vector that points nowhere. Okay, let's move out a little bit. Let's find a point that's a little more interesting. Let's find the point 1, 1. Okay, I plug in 1, 1. What's the vector associated with that point? Well, I would get the vector negative 1, 1. So negative 1, 1. Get that vector there, right? Or what if I plug in the point 1, 0? I get the point 0, 1. I get this vector. Okay, and I can keep on doing that for each point in the plane. If I do it with enough points, I'll get a good idea of what kind of field I have going on here. So let's plug in 0, 1. I would get negative 1, 0. So negative 1 on the x, 0 on the y. Notice for each vector in my vector field, I'm plotting it with the tail of the vector on the point that I'm plugging in. Okay? If I keep on doing this, I'm going to move a little faster. This one would be negative 1 for the x, 1 for the y. I get negative 1, negative 1. I get this. Okay? Let's plug in the point negative 1, 0. I would get 0, negative 1. Let's plug in the point negative 1, negative 1. I'd get 1, negative 1. If I plug in this point, which is 0, negative 1, I would get 1, 0. If I plug in this point, which is 1, negative 1, I would get 1, 1. Okay. And let me just add a couple more just to fill it out just a little more. If I plug in this point here, which is 0, 2, I'd get negative 2, 0. If I plug in this point here, which is negative 2, 0, I get 0, negative 2 as the vector. If I plug in this point, which is 0, negative 2, I would plug in, and just to make it clear what's going on here, I'm plugging in a point, I'm getting out a vector. So let me just illustrate for a couple of them, make sure we understand. So this point is the point 0, negative 2. Okay, so I'm going to plug negative 2 in the whenever I see a y. So I get negative, negative 2 or positive 2 here. And I plug in 0 whenever I see an x in this expression. So in this case, 0 there. Okay, and so the vector is pointing in 2 units in the x direction, 0 units in the y direction. Okay. Maybe just 4 more points just to get our feel for it. So this point is the point 1, 2. So if I plug that in, my first component is negative y, so negative 2. My second component is just the x value, so 1. So I get negative 2, 1. So I'm going to go negative 2 units in the x direction and 1 unit in the y direction. Okay. This point is the point negative 2, 1. So I'm going to plug in, so I'll get negative 1, comma, negative 2. So negative 1, negative 1, 2. Okay, and I'll just fill the rest out of these out real quick, just so we could kind of see what's going on here. It is a little tedious to sketch it out, but hopefully you get an idea of what's going on here. These vectors are swirling around. They are communicating a force. Okay, we often use vector fields like this to communicate force fields. Okay, forces like gravitation, magnetic forces, electric forces, even forces due to a fluid like wind flow or water flow. Okay, and so you could kind of get a sense that if you were in this vector field, how would you be pushed? So, you know, if I dropped a particle right here, imagining that, you know, maybe this is a pond of water, what would happen to this particle? Well, maybe it kind of gets pushed this way. And it kind of spirals out. The vectors get bigger as you spiral out, so it kind of is drifting further away. Kind of what it feels like. Okay? This line here, where we kind of imagine the flow of a particle through a force field, it's called the flow line. Okay? Let me give you a better picture than the one I've drawn. Notice I've only drawn, of course, a few vectors, but every single point in the space has a vector associated with it. I've just drawn a few representative vectors. Let me show you a better representation with more of these vectors so you really get the sense of this spiraling. And if we draw that flow line, oh, it actually doesn't spiral outward. It just stays where it is in a nice circle. It'll flow around and around in a circle. Okay? Let's take a look at a few other vector fields, just so you get a feel for what's out there and what's possible. So here's another vector field. Okay, the vector is determined by these two components. You could ignore the notation on the left side here. It doesn't make sense for us, but these two components are the components of our vector field. So x plus 3y, x minus 2y, the vector field we are displaying here is f of xy equals, what was it? X plus 3y for the first component, x minus 2y for the second component. So for every xy point, this is the vector at that point. Okay? And there's the flow line. I can move the flow line around and see that depending on where I position it, the particle placed in this force field would flow differently, right? Flow line represents the trajectory of a particle that would be acted upon by this force field. Right? Let's see another one. And this one kind of gets stuck. If you look at the flow line, it all flows towards the origin. Here's another one that swirls around, and it swirls outward. Similar, but more stable. Okay, it doesn't, unlike the last example, a particle in this vector field wouldn't flow outward, but it would stay in an elliptical orbit. So all kinds of things are possible. Notice that in practice, when I drew my vector field right here, the vectors kind of all crowded together and got stuck together. Technically, that's correct, but it looks very busy, doesn't it? Here, you'll notice that all of the vectors are the same length, and often we will do that. We will either normalize the vectors so they all have a standard length, or we will just scale them so they have a much shorter length. So the graphical image of the vector field doesn't look quite so busy. Okay. Much like the last one. Now, so far we've only seen two-dimensional vector fields, but a three-dimensional vector field, and let me make sure we're in 3D, three-dimensional vector fields are possible, right? So for this particular vector field here, what do we have? Where are we? We have a first component, a second component, and a third component. So let me just pull this over here so I can read it. In this particular case, our vector field, for each x, y, z point, the vector associated with it is negative x plus 4y plus 2z, comma, 4x minus y minus 2z, comma, 6z. So I just want you to know that three-dimensional vector fields are possible. In fact, many of our most important applications are three-dimensional vector fields: electric fields, magnetic fields, gravitational fields, flow through a fluid. All of these are usually three-dimensional vector fields, right? Three-dimensional force fields. Now, you're looking at this and you say, well, goodness, that's a mess. And you're right. It is very hard to make sense of this. So while technically we can draw or visualize a three-dimensional vector field, it's not very helpful a lot of the time. And so we will usually stick to, if we're going to sketch them, two-dimensional vector fields. If we need a three-dimensional vector field, we usually won't bother sketching them, okay? But we can still think about flow lines through these three-dimensional vector fields. I'll give you a couple more three-dimensional vector fields. Only place the flow line here. Oh, that's interesting. Oh, look at that. Let's see if I can scroll out. That's a Lorentz attractor, if you're familiar with it. If not, don't worry about it. But it's a famous vector field, a famous solution. Okay, so just be aware of what these vector fields are and what they're telling us. You could think of each point in space as having a force associated with it. And the vector is the force acting on any point that would be, or any object that would be at that point. Now, we've actually dealt with vector fields before, we just didn't realize they were vector fields. There's a very important example that we have already dealt with. So say I have some multivariate function, let's keep it f of xy, let's not work too hard here. Okay, so let's say it's a 2x squared sine of xy. If I were to find the gradient of f, that is the vector of partial derivatives. So for x, I'll need a little product rule there, right? So I get 4x sine xy plus 2x squared y cosine xy. That's the partial derivative with respect to x. And now partial derivative with respect to y, I get 2x cubed cosine xy. Notice, and let me change the notation here. To actually include the of xyz. Notice this is a vector field. For every xyz point, actually it should be an xy point, huh? For every xy point, in our two-dimensional space, we have a two-dimensional vector associated with it. So a gradient is always a vector field. Sometimes we call it a gradient field. And it is a very important example, as we will see in coming sections. And I actually have a graph here prepared for that gradient field. Let me pull it over. And there it is. It is really a vector field. At every point, that is its gradient, or the direction of the gradient. I have normalized the lengths. If I don't normalize the lengths, it's a mess. Okay? So I've normalized the lengths. Streamlines are kind of a mess too. There is probably a fair bit of numerical noise, so don't pay attention to the streamlines actually. But you get the idea of what the gradient field looks like here.